We'll start. Welcome to this panel on AI reasoning, hosted by IBM Research Exploratory Science. I'm Murray Campbell, a distinguished scientist at IBM Research, and I'll be moderating the panel today. I've been an AI researcher for many decades, and my early work in AI was in planning and search, which included the development of the Deep Blue chess computer. And my current research interests include the systematic evaluation of the reasoning capabilities of AI systems. The topic of AI reasoning is currently drawing a lot of attention, both in the scientific community and the popular press. There is a belief by some researchers that symbolic reasoning is essential for reliable, verifiable AI systems, while others point to the continuing improvements in the reasoning performance of large language models as a sign that perhaps explicit reasoning is not necessary. And the timing of this panel couldn't be more perfect, given the recent announcement of OpenAI's O1, which is said to be a reasoning model. There's just enough time to see some behaviors without knowing any of the details of what it's doing. Before we dive in, I'd like to introduce the panel members. I think we have an outstanding set of panelists, and I expect they'll bring a variety of perspectives to today's topic. Yejin Choi is the Senior Director of LLM Research at NVIDIA and a professor of computer science and engineering at the University of Washington. She's a MacArthur Fellow, a Time 100 Most Influential People in AI, and a Fellow of the ACL. And Yejin is well known for her pioneering work at the intersection of natural language processing and common sense reasoning. Ernest Davis is a professor of computer science at New York University. His primary research area has been the automation of common sense reasoning for artificial intelligence programs, particularly physical and spatial reasoning. His recent book with Gary Marcus, Rebooting AI, Building AI System, Artificial Intelligence We Can Trust, surveys the state of the art and calls for the development of reliable AI systems with deeper understanding by incorporating insights from cognitive science. Pascal Fung is a Senior Director of AI Research at Meta Fair in Paris and a Chair Professor in the Department of Electronic and Computer Engineering at the Hong Kong University of Science and Technology. She's a Fellow of AAAI, ACL, IEEE, and ISCA. Pascal is best known for her work in developing AI systems that can understand and generate language in more natural and intuitive ways. Rao Kambhampati is a professor of computer science and engineering at Arizona State University and is a fellow of AAAI, AAAS, and ACM. He served as the president of AAAI and is a founding board member of Partnership on AI. He has been one of the leading thinkers in planning and human-aware AI systems for many decades. Thank you all for joining us today. So we'll start with some questions that are mostly independent of any particular technical approach to AI reasoning. Specifically, what is your definition of reasoning? And given your definition, what kinds of applications do you feel will require reasoning to be successful? And we'll start with Yejin.
Thanks, Murray, for organizing this very exciting panel. So my way of thinking about the definition of reasoning is to think about in contrast with knowledge. So we, often talk about knowledge and reasoning. So how do they differ? Knowledge is either a fact or a proposition that is known to be true. So for example, snow is white in general. We all know that. And it's generally just memorized fact that we just need to retrieve. Whereas reasoning builds on knowledge but goes one step further by applying inference rules over a collection of knowledge or facts in order to draw a new conclusion that was not provided by a collection of observation or knowledge that we might have. So given a partial information about the world, we're trying to draw a new conclusion through reasoning. And so, for example, if you see an empty snowfield and then you see footsteps, then even if you don't see anyone, you might infer that someone might have been there before. So this, allows us to think about, see things that's not even visible, or reason about things by connecting the dots. So what application require reasoning? I personally would think, people usually think of math or coding applications as most representative applications of reasoning. But I would say literally every application either require reasoning or at least can benefit from reasoning. So especially when the application might require dealing with previously unseen situations that was not in the training data. And, from our human perspective, just like pretty much any daily activities, like thinking about, or let's just say reviewing paper, scientific paper, or packing a luggage for a trip, then you need to sort your items in the luggage. That's the spatial reasoning. Or selecting whom to hire for a job. This all requires some sort of reasoning. Now, the weird thing about knowledge and reasoning is that the boundary is not very clean cut, because if certain reasoning patterns repeat a lot, you just memorize the answer. So, if I ask you, what is 2 raised to the power of 5, you probably are not going to compute that. You just have a memorized knowledge that it's 32. So a lot of repeated reasoning becomes knowledge, which actually makes this, question of like, how should we approach this reasoning problem quite interesting. So I'll stop there.
All right. Thank you, Yejing. Ernie, would you like to go next, please?
Sure. Thank you. So I don't have a definition of reasoning because general categories don't usually have definitions. I have a number of observations to make about it. First of all, reasoning as a descriptor is originally applied to human cognition, and it's applied to AI programs by extension. And I think it fits better with human cognition. There are things that we can say about AI programs, they are trained on next token prediction, let us say, which don't apply to people, and the reverse is also true. And so reasoning is in humans is a proper subset of Kahneman's system 2, which is a little vague. But the defining characteristics of systems 2, many of them don't apply to computers. For instance, system 2 processes make demands on working memory. It's not a thing that applies to AI programs. That's point 1. Point 2 is that reasoning can apply both to processes, is a descriptor of both processes and of tasks, and is fundamentally of processes. And again, tasks by extension. A reasoning task is one that characteristically involves a reasoning process. And if you can show that an AI or a human is carrying out a reasoning task, then that suggests that it may be using a reasoning process, but it's certainly not decisive. And I would say that reasoning versus non-reasoning is not a dichotomy, it's a spectrum, and it's a multidimensional spectrum. So there are features which are reasoning-ish, as it were. And the kinds of features that you have are sub-steps that are available to conscious introspection in people, inspection and criticism of one's own output, meta-reasoning, invocation of diverse domains of knowledge, the use of non-obvious forms of argument like proof by contradiction and case analysis, use of partial information, use of abstraction, meta-reasoning, use of a complex world model. These are all characteristics, though not defining characteristics of reasoning. What applications do you think require reasoning? I would agree with Ye-Jin that potentially all applications require reasoning. It depends how practiced they are. And as she says, in a very practiced situation, you don't require reasoning. You can do it automatically. Conversely, even with tasks that are generally System 1, like language production is a classic System 1 operation most of the time. I'm not reasoning about what I'm saying, though I thought about it before. If you're speaking a new language, then it may, if you're learning a new language, then you may think through very in great and specific detail about how to put things together to fit with the grammar and the conventions of the language. Vision is a classic non-reasoning task, but of course, image interpretation of difficult images can be very difficult science or scholarship and so on. And it's not clear how this applies to AIs because AIs are not exactly practiced in what they do, and they don't go typically from a state of having to reason through a problem to a state of having to do it, being able to do it automatically. All right, so I'll stop.
All right, thanks, Ernie. And that's one metaphor that we may see from time to time throughout this discussion is the System 1 versus System 2. I think that's pretty clear. Pascal, if you'd like to go next, please.
Yes, I agree very much with Ye-Jin's differentiation between reasoning and memorization, and Ernie's the differentiation between System 1 and System 2. So that sort of cover what I wanted to say, part of what I wanted to say. So I'm going to go in a different direction, provide another perspective. So number one, I think in our daily work in terms of AI research, we tend to have a small set of technical definitions of reasoning, which includes inductive, abductive, deductive, logical and mathematical reasoning, and temporal spatial reasoning, and so on. And then there are various benchmarks on any of these functionalities, capabilities to evaluate our AI systems. However, in the broader sense, if we talk about humans, in general, people would consider somebody who cannot reason or reasons badly to be not very intelligent. So this is kind of, I think, therefore I am. The reasoning is very closely, it's almost like proxy for thinking. So if you can reason, you can think. So in that broader sense, I think it's we have a long ways to go. We don't even have all the benchmarks to cover that. And in fact, indeed, today we don't really have a very, very good and clear taxonomy for what is considered reasoning, independent of other dimensions of intelligence, human or otherwise. But I think, broadly speaking, we do agree that perception does not require reasoning, whereas cognition in general does require reasoning, and reasoning, therefore, in the broader sense, can cover any, even including planning. Right, and meta reasoning, Ernie has mentioned earlier, and many other types of reasoning that's necessary for humans to actually think. So this is an ongoing, I would say, ongoing struggle or ongoing quest for us to define what reasoning is. It's similar to what our struggle in defining what intelligence means. And it's kind of a moving goalpost for intelligent systems or AI systems. Now, what do I think? What kind of applications do I think require reasoning? So actually, my background in the last few decades, I've been building assistants, conversational AI assistants in many different generations of assistants, starting from the early 90s, the Ada system, and later on various voice assistants and so on. Now, assistants, we have them in our daily life. A lot of call centers have been automated by assistants. We're used to voice assistants on smartphones. But today we are looking, with the LLM revolution, we're really looking into more autonomous assistants. So what we call agents. So agents, by one definition, is that are assistants, AI assistants that can carry out multi-steps on its own. So a task that requires human to go to use many steps to accomplish, then agents, our hope that such agents can carry out such tasks by figuring out on its own what is necessary, what knowledge is necessary, what steps it needs to take, and so on. So we can say that to have agents, these systems must have advanced reasoning capability. But agents, they can go anywhere between very kind of atomic capabilities to more sophisticated capabilities. I always use the examples as in my life. Like 20 years ago, I had a travel agent who would, if I tell her that I want to take a holiday with my family, she knows my profile, she knows my budget, she knows my family's, and she asks for a few scheduling questions, and then she figures out the whole thing and gives me proposal and so on. And after, all these smart applications that appear on my phone, booking.com, trip.com, so on and so forth, I've lost her help. I actually have to go in and use all kinds of applications to figure out a trip on my own, which make my life actually more complicated rather than easier. So today we want to have AI systems that will act more autonomously, like agents, like human agents, and figures out how to use its various tools and various information on its own. For that, we require advanced reasoning. And these agents, as you can imagine, they can be in any domain, any part of our lives and work and so on. So that's the direction, and I think we need to develop more advanced reasoning for that.
Great. Thanks, Pascal. Rao, if you'd like to take a shot at this.
Thank you. You can hear me, I hope. Thanks for holding this panel. So I think of reasoning as essentially the ability to solve tasks, problems for which you haven't memorized the solutions. So a meta example is me trying to reason out what I can say that is interesting, given that three very smart people have already talked about what is reasoning. So obviously the system 1, system 2 analogies were quite relevant for that when you are actually able to solve, the first time you wind up solving something from first principles, you tend to remember it so that the next time around, you don't have to start from scratch again. So part of whether or not you would need reasoning depends on your memory, how much memory you have, and how standardized the world is. My joke is that a part of the civilization is standardizing our life, the heck out of the life, so that I would think that as sad as it might sound, the older people like the Neanderthals and co had to reason from first principles more often than I have to when I go through my normal day. I tell my students that the last time somebody actually had to reason from first principles to go through the normal day was when these Colombian kids had their plane crash into the Colombian jungles. There was no Google that they can just figure out, exactly what is supposed to do, when this kind of a plane crash happens. So that's kind of the ability to handle novel things, novelties for you. It doesn't have to be novel for the humanity. If it is new for you, you have to still be able to start from first principles. We have this problem in general when we do interviews of humans, for example, for jobs. They have all mugged up all the possible questions that you have asked other people, and so they come to you with pat answers, and you still know how to figure out whether they are remembering or reasoning by changing the setup a little bit. And so that's the kind of thing that reasoning normally brings up to me in my mind. So it's sort of, it required in learning new skills, learning procedures, following procedures, and also obviously solving things for which you haven't already memorized the solutions. So those are obviously the meta categories where you would need reasoning. The other thing that I would mention is that, of course, I'm coming from planning, and planning, of course, involves essentially looking at a specification and trying to figure out a sequence of actions to kind of reach the goals. Even there, obviously, if you have solved this problem multiple times, you can remember. The interesting thing is the standardization part of planning is much easier to modify because I can just change the amount of resources that are available or the planes that are actually now available, et cetera, and the planning problem changes. And somebody who just mugged up the solution might have a harder time solving the new planning problem. And so for me, reasoning is like very important because oftentimes, even if I actually retrieved a memorized solution, figuring out what it actually works for the current situation requires reasoning too. And the last thing I want to mention is sort of looking into the second part to some extent, I guess, that one interesting thing that blows my mind is AI as a whole has looked at system 2 in the beginning. Mostly what we had was deep and narrow system 2s. Your own Deep Blue is a great example. I mean, clearly it didn't have the kind of memory that was required to remember every possible chessboard configuration and the optimal move that we wound up having much later by the time of AlphaGo. And so you guys actually had to do reasoning. And so one of the things is that we always knew how to do reasoning in automated ways. The interesting question is we sort of figured out how to do system 1 in automated ways more recently, and the question is how to combine these abilities in terms of AI systems. I'll stop there.
Okay, great, thanks. I think we can agree that it's very difficult to precisely define reasoning, and I think we've got some sort of qualitative definitions that we've sort of settled on. And Pascal mentioned benchmarking. I hope we can come back to that topic later. But for the second question or second set of questions, I'd like to ask the panel, focus more on the technical approaches to achieving reasoning. Specifically, can LLMs reason well enough for applications that you care about? And what are the most promising approaches for improving AI reasoning? And again, we'll start with Yejin.
Yeah, great question. So do LLMs reason well enough for applications I care about? Yes and no. I mean, it's surprisingly good in many ways, but it's also making weird mistakes in the most surprisingly in the most surprising cases where, especially for examples where I wouldn't imagine that I would make a mistake, it will make a mistake. There are so many examples, but one example would be something about theory of mind. There has been a lot of debate about whether LLMs do have a theory of mind or not, and at first, when this capability appeared to arise, it was usually more about, there are two people and one object, and, one person goes away, the other person moves this object away, and then the other person comes back, and, do they know where this object is? And there's this particular pattern that tends to repeat in the literature, which LLMs probably read about. So if you tweak the question to make the question a little bit silly, so that you say something about how the person left and then came back, and then you move the object around, for example, while they're both in the room. Then there were periods in the past when that could be the trick to break the LLM behavior, because LLM has this bias about the person didn't see and the person couldn't know. More lately, all of these problems are kind of fixed, it seems. So then we started adding, more people and more objects in the scene. Then, things tend to break again. But one really fun thing that we found is that a lot of theory of mind examples are in narration or narrative of a story that is told from third person viewpoint. But if we ask theory of mind the question in conversation, a trace of a conversation between multiple people, then suddenly this is so hard. For humans, there shouldn't be any difference between two different textual forms, but LLMs will make a mistake. So that's one example where LLMs might make weird mistakes in the most surprising way. Perhaps it's not surprising at all if we think from the perspective of what LLMs has seen during training. But anyway, about the question of what are the most promising approaches for improving AI reasoning, there's a short-term approach versus a long-term approach that may be promising. In the short term, the more data is basically the better. The more traces of reasoning that you demonstrate during training, the better the reasoning capability will be. And I think this is just, in some sense, best we got. It does tend to work pretty well. Only that the corner cases that were not in the training data may not be well covered. But there's one real concern about this approach, which is that LLMs have the tendency to find shortcuts such that the answer may appear to be correct in many problem instances, but by invoking that, it's going to make weird mistakes elsewhere. And so, because the thing about reasoning is that there can be multiple different paths that can lead to the correct answer. And then sometimes some of these paths are incorrect. But LLMs may not know, humans cannot know either, because nobody knows, what really happens in this black box. So as a result, if we really want to solve everything super correctly, maybe just adding more data is not the way to go. Perhaps there could be alternative learning approach where we could really teach the correct reasoning rules. Even better if AI could discover the correct reasoning rules on its own, but not sure whether the current recipe of doing pre-training on massive data followed by RLHF at scale is going to necessarily lead to that. I personally don't believe that's the promising direction.
All right. Thanks, Yejin. Just an interesting note, you mentioned the unreliability. I think there's an interesting Nature paper out today that shows that even the larger the models get, the harder they are to trust for people, because they do well at larger problems, more complex problems, but they still fail on some of the small problems. And that causes trust problems for people. So an interesting paper worth checking out, I think. Ernie, if you wanted to go next on this topic. You're on mute?
Yes, I'm off mute. First, just to follow up on Yejin, a couple of examples of these easy problems that the current technology misses. They still have the current technology, can solve some number of arithmetic problems and arithmetic benchmarks fairly well, but it was discovered rather late that they couldn't count reliably, and now they've gotten better at it, but they still can't count words or letters reliably. So that's strange. Another great example, which I think may actually be due to Rao, is if you take the classic problem of rowing. Yes, McCarthy wrote a paper about this way back, of a guy with a goat and a fox, and he has to row them across the river and so on. And you change it to be trivial. He has only the goat or only the fox and so on. It simply gives its memorized result and doesn't think it through. And there's a wonderful example, Dutier Jin, which let me mention, on drying clothes, where successive versions of GPT did better and better, but never got the idea. So all you had to do was to tweak the problem a little. It would get the problem that you posed it with 2 months ago. But if you tweaked the problem a little and made it slightly more complicated, it didn't get the idea. So let me turn directly to the question of applications that I care about, and can LLMs do it? Well, the application that I care about most over the course of my career has been spatial reasoning, particularly spatial reasoning in the service of physical reasoning. And as far as I can see, the answer is no. I don't see any sign that LLMs can do spatial reasoning reliably. And certainly the video generations do it laughably. They make all kinds of ridiculous, things appear and disappear, and liquid flows through the material of cups and so on. And I'm skeptical that any AI trained purely or primarily on next token prediction, certainly on next token language prediction, will do better. So what can we do to improve this? Well, incorporating multimodal input and learning from that will certainly improve the situation. But it seems to me it makes sense to build in a spatial and a temporal apparatus into the basic structure. And very often, when physicists are using large language models for AIs, deep learning systems for one purpose or another, they do this with considerable care. So the actual structure of the system incorporates what's known about the characteristics of the problem. And I think my feeling is still that despite the remarkable successes of LLMs, that their failure modes are still so striking and pervasive on these basic issues that it's important to consider how a basic structure of the world can be built into their fundamentals.
Great. Thanks, Ernie. Just a quick follow-up to that. Do you think embodiment is necessary for your favorite application, spatial reasoning?
Embodiment will help. I mean, the robot people are using quite different techniques. They rely, first of all, heavily on reinforcement learning, but they also, they have built-in simulators and so on. That's we don't have any roboticists here on the panel. We may have in the audience, but that they're exploring a quite different space of reasoning techniques.
Okay. All right. Thank you. Pascal.
Yeah. So the question is, can LLMs reason? I think that question is almost a proxy for the question, can AI think? I think you ask 1,000 people, 100 researchers, they might get 100 different answers. So, and to me, it's not a yes or no question. Because, we have seen that, first of all, LLM keeps evolving. So we're talking about LLM with RHF or after instruction tuning and various kind of post-processing methods, safety fine-tuning, hallucination mitigation, and so on? Or are we talking about, So broadly, I think people think of LLMs as this autoregressive trained transformer architecture, RHF, the safety fine-tuned model. And usually people think of them as the text-only model and not the multimodal VLMs. So from what I have seen in the past, whenever we say LLM cannot do X, then it can do X. If you can define a benchmark and people can work on it, and then we'll be able to reach that benchmark. We can argue that benchmarks are also just proxies of the capabilities, but that's the nature of research, right? So we build benchmarks and so on. So I would like to cite, for example, there was a benchmark that came out of Meta FAIR called Gaia that tests intelligent systems in terms of tool use and so on, and it was a benchmark that showed that LLM cannot do most of the tasks competently compared to humans, even very simple tasks, right? But I heard that, OpenAI and many companies are working to basically reach the Gaia benchmark very, very soon. So again, if we know the right question to ask, like if we know what reasoning is and we define benchmarks for it, and I'm actually optimistic that we can reach such benchmarks. Now, is that NLM anymore? Like once you have all these kind of additional steps, is that what we call LLM? LLM will remain like the foundational model to our future agentic systems. But would you call them LLM still? At some point, we're gonna, maybe we won't use transformers anymore. Maybe then we won't call them LLMs anymore. So I'm sorry, my answer is not very clear. But what I mean is that it's a moving goalpost, and LLM is not defining one space time. It keeps changing, and different LLMs have different performance, and then as we define more benchmarks, they seem to be able to fulfill or perform to those benchmarks. So I think the most important question is not whether LLMs can reason. To me personally, that's not an interesting question at all, because LLM is not a natural phenomenon that just, it's kind of a natural phenomenon. We don't understand that very well. But to me, as an AI researcher, it is important to work towards solving the reasoning tasks in terms of machine intelligence with whatever tool we have. I saw a question from Francesca asking me, how do we distinguish between benchmark and solving a benchmark and memorizing it? Well, you need to have benchmarks that are not gameable. And then you will look at the details. You can have benchmarks that are not shown. And when we design benchmarks, we need to be careful with this kind of design. So to come up with non-gameable benchmarks and make sure they are not benchmarking something else that's correlated to the ability we're trying to benchmark. So benchmarking itself is a very important research area in terms of, on our path to AGI and on the way we are building our systems. Does that answer your question? Or
yes. Thanks, Pascal. I think we'll probably talk more about benchmarks in a bit. We'll let Rao answer. Before Rao gives his answer, I just wanted to say there's an interesting quote on X by Mark Andreessen. The criticisms of why LLMs can't reason are disturbingly relevant to people as well. I don't know what that says about people, but I think it's interesting and amusing and it's worth thinking about. Anyway, let's move on. Rao, if you'd like to answer the questions of what applications you care about that LLMs can help with or not, and what's the direction forward?
Okay, so let me start by actually answering, commenting on your Mark Andreessen quote. While there may be issues about humans not reasoning, there is accountability. If you fail to reason, and I can show that other humans in that position would have and should have reasoned, I can sue the heck out of you and I can put you in jail. I haven't yet figured out how to put GPT-4 in jail. I've been trying, but I can't find it. So the idea of a super intelligent system that is sort of able to AGI that is able to replace humans, but is fallible but not accountable is something that we do need to worry about. That's why I think this panel is relevant. So coming to LLM's reasoning thing, I will answer it just directly from things that I care about, which is planning. And as I basically, like 2022, we actually just looked at seeing whether the toy planning benchmarks that ICAP's IPC domains use, that's been used from strips onwards from 1972, the blocks world, etc. Can LLM solve them? And we also, when they started, one of the worries that, as somebody pointed out, is benchmark contamination, because we are no longer talking about limited memories or limited training data. And so anything you complain about LLMs is grist for the next LLM training anyway. So one of the questions we had to look at is whether, in fact, so they were doing pretty badly on things like Bloxfold. And we also considered if you change the names, if you just change the name such that dynamics of the problem remain the same. So it's actually the same planning problem, but doesn't talk about blocks, but talks about other terms. Can LLM solve? And they actually just failed pretty badly. And this is consistently has been true for all LLMs that have basically been autoregressive and teacher force trained and RLHF to death. The only thing that the RLHF LLMs will do is they'll be a lot more polite when you point out that they are wrong, because they just know how to make you feel good. So that has been the case as far as LLMs and planning has been concerned. Things are changing a little bit. Basically, as of last Thursday, we have O1 system, but that's no longer the normal kind of LLM. Those of you, and obviously OpenAI has been playing this game of we'll do something, you have to guess what we did by paying them. But the point is, with looking at what they seem to have done, it's very, very different from the normal LLM in the sense they will wind up doing an AlphaGo-like reinforcement learning over chain of thought moves, generic chain of thought moves. This is like doing pseudo RL during the training. That's significantly different from normal LLM training. And then also they do, indefinite amount of inference during execution. At that point, you're essentially throwing in a generalized system 2 on top of a generalized system 1 and can actually pay a lot more. So for example, we just put out a paper evaluating O1's performance on the pan bench, and it shows essentially that while it improves somewhat, it actually takes significantly more money from the poor researchers. We paid basically something like 80 or 100 times more dollars to Sam Altman to test the same benchmarks compared to GPT-4. That's worth remembering. The other thing, of course, is what are the promising approaches? The question ultimately about reasoning is reliability, as you pointed out. I think, as you pointed out, Murray, reliability. Can I trust that the point that when you actually come up with an answer to the reasoning system, is that something that I can trust? And one big issue has been in general with autoregressive LLMs is that we just do not have a good enough mental model of what they can and cannot do. And making lemonade out of lemons has been this word called jagged intelligence. That is, they do what they do well. And if you don't know what they do well, you are in big trouble. That's just not so. That's not true for us in humans. Like if I see a human who can do integration, I can pretty strongly assume that I can take their multiplication results and addition results by trust. Whereas that's just not true for these sort of majorly memory-based systems where it's possible that they're actually being trained on certain kinds of data and not on the other kinds of data. We already know, thanks to work like that of agents, that they won't do multiplication because it turns out that there's only so much you can remember if you're just trying to repeat multiplication just from autoregressive completion. So what are the promising approaches? I'll go back to the point I made earlier. One is that basically we knew in AI how to do reasoning. What we did not know is how to do an effective system 1. So the thing that we want to actually kind of celebrate about LLMs is that they are LLMs, as of before last Thursday, because as I said, this other stuff we don't completely know. They're very different. They're basically adding LLMs on, AlphaGo style things on LLMs. That's an interesting different direction. But LLMs themselves essentially are not able to provide any kind of a guarantee about the solutions that they will provide, they'll give. And we do know how to do reasoning in many different areas. So one interesting thing is to use LLMs as a great generator and use an external verifier, which themselves may be actually built with LLM's help. And this is the kind of thing that in my group we've been pushing. And if we call it LLM modulo. If you look at things like Alpha Proof and Fun Search, etc., that DeepMind did, that's pretty much what they wind up doing. It turns out that math is probably the one last area where you say, this looks, I think it's a proof. Why don't you just, give me a paper? They don't take it, because it has to be, if it's a proof only if it is actually guaranteed to be a proof. And so in planning too, my sense is where actually planning is important, where there actually can be execution failures, the cost of failures can be high, such as non-ergodic domains. You're not just going to be able to take the plans that without any sense of guarantees. And so my way of thinking about it is the promising approaches would be using these sort of technologies as pretty impressive generators, putting them in loops with the kind of verifiers that we have developed beforehand and which also we can improve with the LLMs themselves. So I would sort of think that would be a good direction to look at. Of course, once you have the verifier outside, you can also try to push the verifier in. In fact, Marvin Minsky is famously said, all of intelligence is pushing the test part of generate test into the generate part. And the question, of course, is the current idea for doing that up until now has been just fine-tuning. That's just a very low quality approach. It just doesn't generalize well enough. We have done multiple studies showing that, or other people have done that. But the idea of actually sort of inlaying some kind of a pseudo move RL, after the pre-training part, which essentially, O1 seems to be doing from whatever little I can read, is an interesting direction. But again, we found in our approaches, in our experiments with O1, that it is better than the other LLMs in terms of post-facto correction, evaluation of accuracy, but it's still nowhere near 100%, and it's also not guaranteed. The other difference is a thing about a sound verifier in the loop is if it lets the solution through, you can be sure that the solution is correct, whereas that's just not the case with LLMs. And so again, if failure matters, if actually reliability matters, we do have technologies which will actually combine these things, and I would think that would be a promising way to go forward. Thank you.
Great. Thank you, Raul. So I think at this point we've asked and answered the first couple of rounds of questions. I wanted to, before I dive into another topic, I wanted to see if any of the panelists had any responses to anything they've heard today, that any points that they wanted to make on top of what they've heard. Not yet.
Maybe.
Well, I really... Sorry. Go ahead.
I think we just went from 0 to 3 at a very high speed. We'll start with Ernie. Could you comment first?
Well, I just want to say I really like the quote from Minsky that Rao brought forward. I'd never heard that. I think it's as regards the systems that use the LLM to generate answers and then check in Lean or whatever. I think that's exactly or generate code and see if it runs and so on. That's exactly the issue. You need a much more tightly integrated system at the generation stage, and you need to bring all the intelligence, or at least some of the understanding that's in the verifier, into the LLM. I don't know how that's best done. I don't know.
Thanks, Pascal.
Yeah, I wanted to comment on both this part. I would say nobody's building, using LLM directly in consumer facing products, right? Unless you're using, for example, like if I'm using a Meta glass, I shouldn't want any smart glass, for example, or in the robot, and very unlikely you're going to just use a raw LLM and just have people prompt it, because that's just not the modality, and it's just not practical. And as I mentioned earlier, like agentic systems just going to cover more and more of that, like so people don't have to. Today we know that when people prompt differently, you are likely to elicit different behavior from LLM. And somehow this prompting, and it's not just in terms of, and it's not very intuitive to us, because if you prompt slightly differently with the same meaning, you expect to have the same behavior, but that's not the case, right? So there's a kind of thing. So today, when we build any end-to-end system, we're already building more guardrails, we're building more modules, we're building factuality checkers, we're building safety guardrails, so on. So that goes without saying, I think, for products. But the other thing that I think, and of course, to develop system further, we want to have models itself, like that can have, for example, it would be safe to begin with, and it will be more transparent and more explainable, and so on. So we need to work towards that, and we need to work towards more efficient architecture in terms of training and so on. Now, the other comment I want to make is about the embodied part. And does it need embodiment? So depending on what kind of application I'm talking about. So if we're going to have robots, what we want in the future is that robots that can learn in the physical environment, like humans, how to perform different tasks. And so that kind of learning will be embodied learning, because it's going to be equipped with sensors and multimodal inputs and perceptions and so on. And it will learn more efficiently than if it's just, one modality. So, so I guess for me, because my background is engineering, so I always seem to think of these questions as a challenge and as a goal we need to reach. And again, I feel like asking the right question, like such as do we need embodiment and so on, is very important, on the road to improving intelligent systems.
Thank you, Rao.
Yeah, so I wanted to comment on something that came out multiple times, which is a very fair point, which is how do you test pre-trained systems whether they have whether they can do certain tasks reliably. And one thing that I would certainly make a point about is our general idea up until now has been to use the same kind of tests we use for humans to actually give it to the LLMs. That just makes no sense. In fact, the whole point about LLMs doing well on standardized tests doesn't tell me anything other than the fact that if humans had infinite memory, approximately, basically indefinite amounts of memory, they probably need to do much less reasoning, even less reasoning in day-to-day tasks. So the question of how to actually come up with interesting benchmarks and that you can actually provide is a very relevant thing. And the tricky part is it's almost like a research issue, because the tricky part is we do this in terms of interviews. As I, going back to my other example earlier, when you're interviewing somebody, you're always trying to figure out whether just prepared for the interview or whether they have the ability to deal with problems that will come their way later on. And you do this somewhat interactively, because in essence, based on their answers, you would sort of change the question a little bit to see whether or not they're actually able to reason. That's what you would need to do for even LLMs. But we wind up doing this, like, the mystery blocks for domain is like a thing that was done before, that we basically did, but we're doing it beforehand. Is there a way where, oracular benchmarks, which will actually modify the problem to actually check whether there's reasoning going on, is a very interesting topic. And I'm not sure whether that actually makes it even harder, because you need like a super AI to just even get an AI. But it is worthwhile understanding that most of these multiple choice questions, that just breaks my heart to think that the way to evaluate reasoning has become multiple choice questions on huge benchmarks. Most of these benchmarks have been saturated the heck out. And it's mostly because you don't need to actually answer. I mean, in fact, there's been work on normal LLMs that showed that if you remove the question, they still get the answers right. That's the level of pattern matching that happens essentially when you have significant amounts of memory. I think these are great things, but if you want to evaluate them correctly, we need to avoid the pitfall of using the same thing that we are using for humans to evaluate whether they can reason. And we have to come up with better techniques, etc. That's kind of a very important thing.
Yeah, I agree. I think we need to think a lot about the mechanisms we use for evaluating and benchmarks in general, especially around reasoning. So the time has flown by. We only have 5 minutes left. I would ask each of the panelists to maybe give a 1-minute summary of their feeling about the directions forward for reasoning, what they care most about reasoning, what they think needs to be addressed by the research community going forward. We'll start with Ye-Jin.
Yeah, great discussions so far. Perhaps I would like to add one summarizing sentence about the evaluation challenge. I think it's one of the most important research questions that we face today, which is how do we evaluate AI systems? And traditionally, we used to think that humans know how to test AI systems by writing out problems, but I begin to believe that there's a real challenge in relying on human intelligence only in testing AI capabilities, because humans usually have cognitive biases, and also they tend to have like similar biases across many different people, such that they just ask the same things, and then it then becomes part of the future iterations of RLHF data, and we don't know for sure whether the benchmark that the task that a benchmark represent is truly solved or not. So in the coming years, I envision that evaluation will become increasingly challenging, especially if we want to have a firm grasp on the true reliability of the system. And it might be that we need an AI system or algorithms or some sort of like adversarial inference time algorithms that can really explore the space of all the problems, including unknown regions of the problems, that can discover the weaknesses of these systems. And this might be especially important for in the future when AI systems will become even stronger, very fast, at an uncomfortable speed, I suspect. And people will increasingly rely on it. And especially, maybe forget about benchmarks, especially when, AI systems are actually used with long input text and long output text, or, images mixed in or spreadsheet mixed in. And in that situation, robust evaluation becomes even harder. And there's a question of like, what can we possibly do about that?
Thank you, Ye-Jin. Ernie, if you could give your wrap up maybe in a minute or so.
Yeah, quick. First of all, I very much want to give a +1 to Rao's comment that tests designed for humans are not good for AI. And this is particularly true for a lot of the math benchmarks. Second, you want to keep in mind you can't necessarily foresee how AI is going to cheat on a test. And the classic example here is Clever Hans. There was no reason before Clever Hans to suppose that the test, if you ask a horse to do arithmetic and it taps out the right number of the right answer in its hoofs, that it will get the wrong answer. That seems like a perfectly good test. And before you do it, there's no reason to have the person who knows the answer be somewhere else. So you have to, you can't predict all the ways that AI may cheat on a test. And how you have to respond and examine as the AI comes up.
Thanks, Ernie. Pascal?
Yeah, I think also that benchmarking is one of the more important. I think I've said many times during this panel that it is very important to work on benchmarking methodology. And Yejing and Ernie both eloquently expressed why. And I think the one reason we see so many kind of human intelligence tests kind of benchmark for AI is because they are more explainable to humans. Simply because like people want to understand when they say are LLMs or AI intelligent, they're comparing themselves to it, right? So that's just human nature, and that will have to stay, explainable benchmarks, because we need to show to the users, we need to show to developers, we need to show society certain capabilities. Now, so explainable benchmarks will remain important. And other things, we today don't have a full grasp on the full scope of theoretical grasp on the scope of LLM capabilities, because we don't really understand these models thoroughly. So I would say that another very important direction that some people are today working on and is the, some people call it physics of LLM or science of LLM, which is to understand the, mechanical understanding of this neural network and see what they're doing with different probes. And some are working on, looking at their parallel with human brains and so on. So it's almost like studying the neural artificial brain. So I think that's a different direction of research that I think is very worthwhile taking. Even as scientists ourselves, I know earlier I said I'm an engineer. Sometimes I'm a scientist. Like our curiosity is such that we want to understand what these models, why they have such capabilities and how different they are from humans. And I think that's another very important direction to go in terms of research, and the beneficial use of how can we theoretically guarantee safety of such models is also a very important research direction.
Great, thank you. Rao, we'll let you have the last word today.
Thank you. So I think the question of whether large pre-trained models, mostly trained on memory without any reasoning process, inbuilt, which I'm still talking about as the most of the LLMs pre-last Thursday at any rate, whether they can show reasoning patterns once in a while, I think that's answer is yes, they can, because sometimes, by just, for example, I joke around that I have top two answers. In my top two answers, I have the correct answer for every true false question in the world. And it's just, I don't know which one is the right one. So ultimately, if you want these systems to be accountable, there needs to be some way of providing some semblance of guarantees. We have gone, interestingly enough, very far from an algorithm is not an algorithm, it fails on one case, to an algorithm is an algorithm. I mean, a system is a system if it works well on almost memorized benchmarks. I think LLMs are great generators, and they might very well generate very interesting reasoning solutions, but there needs to be some sort of a way of guaranteeing within the training itself or outside as an external verifier. So at the risk of kind of saying something probably that will make me feel bad later, I will say, like Reagan said, trust but verify. So let LLM say what they want, but you should be able to verify outside. Otherwise, one of the biggest issues is you use systems for in cases where you don't already know the answer. I mean, I don't know how many of you use Google to check whether Sergey Brin and Larry Page know the answer to the question. That's not what we use Google for. We use Google to actually check the answers for which you have no idea what the answer looks like, and you want to trust that it actually gave the right answer. It's the same thing for reasoning. And so if you want to get there, you really should be able to have some notions of guarantees built in. As again as saying, it just has some percentage on benchmarks. And so that's where I think we will be going. And I think it'll be a great, I don't see any reason we won't get there, but I don't want a premature celebration. We, at least according to Sam Altman, at least we have 1,000 days. So June 20th, 2027 is when AGI is going to come. Up until then, we are fine. Okay, thank you.
All right. I wanted to wrap up and thank all the panelists. This was a fascinating discussion. I think if there's any grad students who've been listening very carefully, I bet they'll find a whole host of thesis topics in the stuff that we've talked about today. So thank you again to everybody, and I hope you enjoyed it. Bye.